Welcome to this explainer. Today, we're going on a macro to micro journey, straight into the heart of the machines that literally run our world. We'll start with the big picture of how computing evolved, and then we're going to slowly zoom all the way in to the microscopic operations happening millions of times a second inside the device you're using right now.
So, let's kick things off with the ultimate question. How exactly did humanity leap from counting on simple wooden beads to building artificial intelligence that can actually learn, reason, and solve problems completely on its own? It seems like pure magic, but it's actually a beautifully logical progression of engineering.
Here's our roadmap for the teardown today. We'll breeze through the evolution of computers, compare natural and artificial systems, break down the physical anatomy, dive into the von Neumann architecture, explore memory and storage, and wrap up with hardware and software engineering. Let's get right into it.
Section 1. The Evolution of Computers, from the Abacus to AI. It's honestly an incredible leap. We're talking about starting in the 1940s with massive, power-hungry vacuum tubes. Then, the 1950s brought us smaller, much more reliable transistors. By the 60s, engineers figured out how to squeeze multiple transistors onto single integrated circuit chips. That sparked the microprocessor revolution in the 1970s. And today, we're fully deep into the fifth generation, focused heavily on AI, natural language processing, and robotics.
Just imagine trying to build a modern smartphone using those massive, fragile glass vacuum tubes. They were notoriously slow, super unreliable, and just drained power. Compare that to a modern microprocessor, which integrates entire processing units under a single microscopic chip. It was a total game changer in terms of blistering speed and compact size.
All right, Section 2. Natural versus artificial systems and understanding what a system actually is.
At its core, a system is really just a bunch of interconnected parts working together to get something done. But there's a pretty massive divide here. Natural systems, think of a forest ecosystem or the water cycle, they're totally self-regulating. They evolve autonomously using natural energy. On the flip side, artificial systems like the computer you're on right now are entirely human-designed. They completely depend on us for power, updates, and physical maintenance.
Moving on to Section 3, the anatomy of a computer and its physical components.
It's really fascinating how we interact with these machines because there's a really clear divide. You've got your input devices, the things we actually touch to feed instructions in, like keyboards, mice, and mics, and then you have your output devices, the monitors, printers, and speakers that take all that processed data and translate it back into something we humans can actually see, read, and hear.
Pop open the case and you'll find the motherboard. You can really think of this as the biological nervous system of the machine. It's the central hub containing slots for memory and sockets for the processor, and it connects absolutely everything. Every single command and piece of data has to travel right across this board.
Section 4. The von Neumann architecture. This is the true brain of the machine.
So, here's the crucial turning point. Back in 1945, a brilliant mathematician named John von Neumann introduced the stored program concept. Before this, you literally had to physically rewire computers just to run different programs. Crazy, right? Von Neumann realized that both the instructions and the data should live in the exact same memory. And wow, this incredibly flexible design is literally still the foundation of almost every single computer made today.
When you break down that architecture running inside your device right now, you've got the central processing unit, the CPU, or the brain, which houses an arithmetic logic unit for crunching math, and a control unit to manage the flow of activities. And it talks to the memory using pathways we call buses. You've got an address bus to locate the data, a data bus to actually move it, and a control bus for commands. They act exactly like arteries pumping the lifeblood of data throughout the whole system.
All of those pathways make the instruction cycle possible. This is the absolute heartbeat of your computer, an endless, blistering fast three-step loop. Step 1, fetch the instruction from memory. Step 2, decode it so the control unit knows what it means. And Step 3, execute the operation. Fetch, decode, execute. Millions, even billions of times a single second. It's just wild to think about.
Okay, Section 5, computer memory and storage. Let's talk about where all that data actually lives. To really wrap our heads around the massive scale of data, we have to start at the absolute bottom. Everything ultimately boils down to a single binary bit, just a 0 or a 1, basically a tiny switch that's off or on. Group 8 of those together, you get a byte, which holds a single character, like the letter A. From there, it just scales exponentially. You jump up by factors of roughly 1,000 into kilobytes, megabytes, gigabytes, all the way up to those massive terabytes and petabytes.
Now, a super important distinction here is how memory deals with power. Volatile memory needs a constant, steady stream of electricity. If the power drops, it instantly forgets everything. It is strictly for temporary storage. Non-volatile memory, on the other hand, remembers everything permanently, even when your laptop is completely powered down and sitting in your backpack.
So RAM, or random access memory, acts as the computer's volatile, short-term workspace. When you boot up a game or open a web browser, the system loads it right into the RAM so that blazing fast processor can get to it instantly without waiting around. But again, the second you power off, that workspace is wiped totally clean. For the long haul, the system uses secondary storage, which is your non-volatile memory. Modern rigs mostly use solid-state drives, or SSDs, relying on super-fast semiconductor chips. But you've also got traditional magnetic hard disks, which actually use a physical read-write head hovering over a spinning platter to alter magnetization. That's what permanently locks in those ones and zeros, keeping your photos and documents totally safe.
And finally, Section 6, Hardware and Software Engineering, how we actually bring all this to life.
Software engineering is all about creating the invisible instructions that wake the machine up. We usually split this into two buckets. First, system software, like Windows, macOS, or Android, which acts as the overarching manager for the hardware. And then you have application software. These are the specific, purpose-built programs you actually interact with, like the web browser or media player you're using to watch this explainer right now.
Then on the flip side, you have hardware engineering, which is the physical construction of the machine. These are the folks designing incredibly complex digital and analog circuits. They're working on integrated circuit design to pack more and more power into CPUs, and they're the ones dreaming up that overarching computer architecture, figuring out the absolute most efficient ways to route data through physical constraints.
So, having journeyed all the way from ancient wooden abacuses through massive hot vacuum tubes, right down to the microscopic lightning-fast fetch-decode-execute cycles of a modern chip, I want to leave you with this one thought. As artificial intelligence continues to rapidly push the boundaries of what these systems can actually learn and process, what on earth will the next revolutionary generation of computer architecture look like? Thanks for joining me on this explainer, and definitely stay curious.